Problem 4.3.28. Solve the higher order differential equations using Laplace transform. So y double prime, we have coefficients of 1 in here. So we have 1 times s squared y of s minus sy of 0 minus y prime of 0. This whole thing is for double prime. And then minus 4 single prime sy of s minus y of 0. And then plus 4y of s. Now for t cubed times e to the 2t. So for the Laplace transform of Tn, that is n factorial over Sn plus 1. Right? That's 1. And then also the first translation theorem said Laplace transform of e to the at f of t equals f of s minus a. Laplace transform of t cubed equals 3 factorial over s to the 4. And then Laplace transform of e to the 2t times f of t, that is f of s minus 2. So using these two, that is 3 factorial is a 6 over f of s minus 2. So s is s4, so s minus 2 the power of 4. Use this initial condition. They're all 0 initial conditions. This is going to go all away. Then we have s squared y of s minus 4 s y of s plus 4 y of s 6 over s minus 2 to the power of 4. If you factor out y of s, we have s squared minus 4s plus 4 y of s equals to 6 s minus 2 4. And this is s minus 2 squared, right? Now y of s equals 6 over s minus 2 power of 6. Now inverse Laplace transform of this. If you have a power of 6, that means we have to have y of s equals s minus 2 6. For the numerator, we have to have a 5 factorial, right? That'll give us t to the power of 5. And then we still have 6, and then we need to divide 5 factorial so that we can have the exact same equation right there. That means we don't want to touch this 5 factorial. And then we have a 6, 5 times 4 times 3 times 2 times 1. And we have 6 and 6 cancel that out. So now we have 1 over 20, 5 factorial, s minus 2 the power of 6. Inverse Laplace transform y of t equals 1 over 20 times this whole thing, just like what we saw, is a t5, and then first translation s minus 2 will give us e to the 2t. So if you're not going to use this Laplace transform for this higher order differential equation, what we learn in chapter 3, we can use undetermined coefficients technique in here. So in chapter 3, we use undetermined coefficients technique to solve this higher order differential equations. How did you do that? We need to find the ox equation first, and that is m squared minus 4m plus 4 equals to 0, m equals to 2, m equals to 2. Therefore, y of c equals to c1 e to the 2x plus c2. we cannot use the same one, so we need to multiply x to the 2x. Now for yp, we can assume that as ax cubed plus bx squared plus cx plus d e to the 2t. And when we try, it's not going to work. And this is not going to work by looking at it because of this, right? Cx e to the 2x plus d e to the 2x. There's a repetition, right? That and that. So we cannot do that. That means we have to choose yp as ax5 plus bx4 plus cx3 plus dx squared, because we don't need to have x term and constant term. So if you use this yp, and then you need to find yp prime, you need to find y double prime, and put that up into y double prime plus 4 times yp prime plus 4yp, and then let that equal to x cubed e to the 2x. And you go through all of this, you end up getting a equals to 1 over 20, which is the same as what we had here. But this process is going to be really long. Much easier to use Laplace transform to find the solution.